In this section, we will discuss one more example on how to use dimensional analysis and scaling analysis. For that, we will take the example of the drag on a sphere. So let's assume that we have a sphere. The sphere has a radius A, and it is moving in a fluid. We'll assume the density of the fluid to be rho, and the viscosity, the dynamic viscosity, to be mu. Now the sphere is moving at a constant velocity, capital U, and the question is to find a non-dimensional scaling law for the drag. A non-dimensional scaling law for the drag. So that's our question. Alright, so there are two approaches to that. We'll first look at how do we approach the problem with dimensional analysis. And so for this, we first need to identify the relevant physical parameters. And here again, dimensional analysis doesn't tell you what are the relevant physical parameters, so you really have to find them yourself, but usually they're really given into the problem. So clearly u, the velocity, is going to be a relevant physical parameter. A is going to be a relevant physical parameter. The dynamic viscosity, the density, and then is that all? No, of course we want to find a non-dimensional scaling law for the drag. So we're looking at the drag on the sphere. So drag is also a physical parameter. So how many do I have now? I have m equals 1, 2, 3, 4, 5 relevant physical parameters. Now I need to count my units. Well, what are the units that I have here? Velocities are meters per second. The radius is in meters. The kinematic viscosity is in kilogram meters minus 1 second minus 1. The density is in kilograms meters minus 3. And the drag is in Newton, but Newton is not an independent unit. So the drag is in kilograms meters second minus 2. So we have kilograms, we have meters, we have seconds. Those are the three independent units that we have. So n equals 3. So now from the Buckingham pi theorem, we'll say that the problem can be described in terms of m minus n equals 2 non-dimensional numbers. Now, what are these numbers? Again, there is no unique way of defining these numbers. And so there are different ways of doing that. In your Kundu book, in chapter 111, they describe a systematic way of finding those non-dimensional numbers with dimensional matrices. So I refer you to this chapter for this systematic method. I tend to not do that, and instead, with pre-knowledge of the kind of non-dimensional parameters which I want, just find my own non-dimensional parameters. So let's start with our first non-dimensional parameter. Right, and here I need to think, I want the first non-dimensional parameters because I'm looking at a non-dimensional scaling law for the drag. I want drag in my non-dimensional parameter, and if that's the most important physical quantities, then I'm going to take it to a power of 1 in the denominator. So pi1 is going to have the drag in the numerator. So drag has units of kilograms, meters, second minus 2. Now if I want to form a non-dimensional parameter, I have to cancel the kilograms which are on the numerator, and so I have two choices. I can either cancel those kilograms with the viscosity, or I can cancel it with density. Now, dimensional analysis, Buckingham pi theorem doesn't tell you what to do. If you cancel the kilograms with the viscosity, you'll get one non-dimensional numbers. If you cancel it with density, you'll get another one. And no one is there to tell you which one is the right one. You have to, based on physical intuition or based on what people usually do, you pick one, and in that case, you're better off picking the density. If for any reason you pick the viscosity, that would be no problem, but usually you would pick here the density. So I'll put the density here in the numerator, and if I want to cancel kilograms, then I need to put it to the power of 1. So I'm putting rho here, and that means that I'm dividing here by kilograms times meters minus 3. Alright, so I neatly canceled my kilograms here. Now I could look either at my meters or at my seconds, and what I will do here is I look at my seconds. If I want to cancel my seconds, I already used the drag, I already used rho. If I try to cancel my seconds using the dynamic viscosity, then I'm reintroducing kilograms. So I don't want to do that. So my only choice is to cancel my seconds with the velocity. And since I have seconds to the minus 2, I need to put in my denominator the velocity squared. So here I put my velocity squared, which means in terms of my units, I have a meters second minus 1 squared. Now you see that my seconds nicely cancel, right? And here, what units am I left with? I have meters minus 3 times meters, so I'm left with 1 over, here I have 1 over meters squared. And so if I want to cancel this, I simply have to multiply here by a length scale squared, and the only physical parameters that I have with just length scale, with just meters, is a. So I have to multiply by a squared. All right. And so here I have my first non-dimensional parameter, which I take m squared. So this is now non-dimensional. All right. What is this non-dimensional? What does this non-dimensional parameter represent? Right, you will recognize that this looks like a drag coefficient. So here, this looks like a drag coefficient. All right, so I have my first non-dimensional group, and now I need to find my second one. All right, so in this first non-dimensional group, I used d, rho, a, and u. So I know that to have two independent non-dimensional groups, I need to have in my second one the dynamic viscosity. So it needs to be in. Now, dimensional analysis again doesn't tell you how to form your non-dimensional group. Now, I will tell you, it would be weird to say I want mu to be, that mu is such an important parameter in my non-dimensional number that I will put it in the numerator, because it's very hard to change that one experimentally. The one non-dimensional, the one physical parameter from all of these parameters, which you can really easily change in your experiment, just think about an experiment in the wind tunnel, is u. So actually the one parameter which you do want to have on the numerator would be u. So I'll start my non-dimensional number with u in the numerator, and that gives me as units meters per second. Okay, so we start the game again. We need to cancel our seconds, and now I told you that I need to have the kinematic viscosity in my non-dimensional number. So I could try to cancel my seconds with either mu or the drag, but really I'm going to pick mu to make sure I have independent numbers. So if I want to cancel a 1 over a second, I need to put the dynamic viscosity in the denominator. And so in terms of units now, I have in the denominator kilograms, meters minus 1, second minus 1. So I nicely cancel my second minus 1s. So now I need to also cancel my kilograms. Now what do I have available? I could cancel my kilograms with the drag, or I would cancel my kilograms with rho. But if I cancel them with the drag, again, I reintroduce the seconds, and I don't want that because I've gotten rid of this unit. So the only choice I have is to cancel my kilograms with the density. So I'm going to go ahead here and put the density on the numerator, rho. And so here I have multiplying by the density, kilograms meters minus cube. My kilograms cancel, and now I only have to balance my units of meters. And what you have here is that you is a static pressure. So you recognize that your drag coefficient is the ratio between a force, your drag, and a static pressure times a surface. And your Reynolds number is a ratio of the effect or of the inertial forces to the viscous force. But this one we will see many, many more times. And so finally the answer is we wanted to look at a scaling law for the drag. And so from Buckingham Pi's corollary, we know that we can write that one of the non-dimensional parameter would be a function of the other. So we know that pi 1 is going to be a function of the other, and therefore what we would write is that our drag coefficient, d divided by rho a squared times u squared, is going to be a function of our Reynolds number, rho a u divided by mu. Now, usually a drag coefficient you will write as CD, and the Reynolds number you usually write as RE. So our non-dimensional scaling law is just CD, the drag coefficient, is going to be a function of the Reynolds number. That tells you, in this problem, you vary the Reynolds number here, so you will change the drag coefficient on the sphere. But dimensional analysis doesn't tell you what this function here is.